When a nuclear reactor fails, the containment vessel is the last line of defense. Steel and concrete, meters thick, designed to keep radiation inside. Windscale Pile Number 1 was built without one. Air goes in, air comes out. That was the entire cooling system. 416 kilograms every second, drawn straight through the core and out a chimney into the open sky. No sealed loop, no wall between the reactor and the world outside. On October 10, 1957, that chimney released 20,000 curies of radioactive iodine over the farms of northern England. A hospital thyroid treatment uses 15 millicuries. This was more than 1,000,000 times that. This is the story of a reactor cooled by the one thing that feeds fire. In the years after the Second World War, Britain needed a nuclear deterrent. But the 1946 McMahon Act had severed all nuclear cooperation from the United States. The Americans had vast deserts and unlimited budgets. Britain had neither. The American plutonium reactors at Hanford sat in the middle of a desert, surrounded by 50 miles of empty land in every direction. If the same buffer zone were applied to Britain, almost all of England and Wales would be disqualified. So water cooling, the safer option, was ruled out. A water leak in a densely populated island could not be contained. Air could. British engineers built what the geography allowed. 2,000 tons of graphite blocks stacked into a horizontal cylinder 15 meters across, threaded with 3,444 fuel channels loaded with natural uranium metal. Air, ordinary air, was drawn in through the front face by massive fans, passed over the fuel, and exhausted through a chimney 130 meters tall, directly into the atmosphere. No containment vessel and no sealed cooling loop. Just air in and air out. It was cheap, it was simple, and for 7 years it worked. By 1957, the reactor had been running for 40,000 megawatt hours. And the graphite had a problem. When neutrons strike carbon atoms in a graphite lattice, they knock them out of position, creating microscopic defects that store energy. Physicists called this Wigner energy, after the Nobel laureate who predicted it. Left unchecked, it accumulates, up to 2,000 joules per gram. Enough to heat the graphite by several hundred degrees in an instant, without any external source of fire. 2,000 tons of it, all storing that energy. The only way to release it safely was to heat the graphite to around 250 degrees Celsius, allowing the displaced atoms to snap back into position. They called this procedure annealing. On October 7, 1957, the operators shut down Windscale Pile Number 1 for its 9th annealing cycle. It would be its last. The fuel inside Windscale's core was natural uranium metal, 72,000 cartridges of it, threaded through the graphite. And uranium has a property that most people never consider. It burns. Expose metallic uranium to oxygen at temperatures above 250 degrees Celsius, and it oxidizes. Violently, exothermically, and once started, almost impossible to stop. 250 degrees Celsius. That was also the target temperature for the annealing procedure, the very process designed to keep the reactor safe. The temperature needed to release Wigner energy safely? 250 degrees. The temperature at which the fuel catches fire? 250 degrees. The margin between safety and catastrophe was 0. And the uranium was not alone. Each fuel cartridge was sealed inside an aluminum casing with cooling fins designed to dissipate heat into the passing air. But in 1955, engineers had shaved 1.6 millimeters off each fin tip, a modification to reduce neutron absorption and increase plutonium production. The cooling efficiency dropped. Local hotspots became harder to prevent. And there was one more element in the core that was never part of the original design. Britain's hydrogen bomb program required tritium. To produce it, lithium-magnesium alloy cartridges had been loaded into the reactor, a material that ignites at temperatures lower than uranium. Natural uranium with a 0-degree safety margin. Cooling fins deliberately weakened. A foreign alloy that burns at lower temperatures than the fuel itself. The reactor was not just carrying fuel, it was carrying an accelerant. So the fuel was waiting. But fuel doesn't ignite itself. For that, you need a trigger, and a system that can't see it coming. The operators had one job during annealing: watch the temperature. But the instruments were watching the wrong place. The thermocouples, the reactor's only temperature sensors, were positioned at the front face and lower center of the core. These locations reflected where temperatures peaked during normal operation. But annealing was not normal operation. During Wigner energy release, heat builds unevenly, in isolated pockets scattered across thousands of fuel channels. The sensors could not see them. On October 8th, at 11:25 in the morning, 34 hours after shutdown, one thermocouple showed something unusual. Channel 20/53 was climbing at 10 degrees Celsius per minute. The safe rate was less than 5. But on the control panel, the surrounding channels showed temperatures falling, as expected. One channel rising at twice the safe rate. Every other reading on the panel declining. The operators concluded that the Wigner release had stalled. At 5 o'clock that evening, they initiated a second nuclear heating. They pushed more energy into a core that was already on fire in a place they couldn't see. And there was no one to stop them. The thermocouples showed a safe picture. The scanning gear, designed to detect fuel damage, had jammed from thermal distortion. The safety review had been conducted by the same organization that operated the reactor. No independent regulator existed. Under the 1954 Atomic Energy Authority Act, the operators, the designers, and the safety inspectors all worked for the same institution. Sovereign immunity shielded the facility from local fire codes, public health regulations, and external oversight. The instruments said the reactor was cooling. The reactor was burning. And no one outside the fence knew. By the morning of October 10th, the chimney's radiation monitor spiked, 6 curies above normal. Something inside the reactor was releasing radioactive material into the exhaust. At 4:30 that afternoon, 87 hours after shutdown, an operator climbed to the charge face and looked directly into a fuel channel. The uranium was glowing cherry red. 150 channels were on fire, with an estimated 11 tons of uranium ablaze. The response was instinctive: open the dampers, increase the airflow, cool it down. 416 kilograms of air per second flooded into the burning core. Air contains oxygen, and oxygen feeds combustion. The cooling system had become a bellows. The dampers opened, the fans accelerated, the fire surged. The chimney radiation readings climbed beyond anything the instruments could measure. They tried carbon dioxide, pumping it into the core to smother the flames. But at 1300 degrees Celsius, CO2 dissociates, splitting into carbon monoxide and free oxygen. The fire extinguisher had become another source of oxygen. The cooling system fed the fire. The fire extinguisher fed the fire. There was only one option left: water. But water and uranium at 1300 degrees produce hydrogen gas. And hydrogen, in the presence of oxygen and heat, explodes. To use water, they first had to remove the oxygen entirely. At 10 minutes past 10 on the morning of October 11th, the shutdown fans were sealed. Airflow dropped to 0 kilograms per second. And then they opened the water. 1,000 gallons per minute, poured onto a reactor core at 1300 degrees with no certainty that it wouldn't detonate. It didn't. The fire began to die. It was 5 o'clock in the evening on October 8, 1957. Channel 20/53, deep inside the core of Windscale Pile No. 1. The fuel, natural uranium metal with a self-ignition temperature of 250 degrees, cooled by fins that had been deliberately weakened, surrounded by lithium-magnesium alloy that burns at even lower temperatures. The trap. Thermocouples positioned for normal operation, blind to the hot spots of annealing, feeding operators a picture of safety while the core burned in their blind spot. No independent regulator, no external check. The path. An open-cycle air-cooled reactor where the cooling system draws oxygen directly across the fuel and exhausts it through a chimney into the open sky. A system that, in a fire, becomes a 416 kilogram per second bellows. In that configuration, the physics had only one outcome. The operators saw a temperature drop on their instruments. They added more heat. The reactor reached 1,300 degrees and the uranium melted. The chimney carried 20,000 curies of iodine-131 across 500 square kilometers of English farmland. And the cooling system worked exactly as designed. It moved air. Milk from 500 square kilometers of farmland was seized and destroyed. Iodine-131 concentrations in local dairy reached 29.6 kilobecquerels per liter. The emergency limit, hastily set during the crisis, was 3.7, 8 times over. There were no immediate deaths, but decades later, epidemiological studies estimated that between 33 and 100 people developed fatal cancers from the fallout. The investigation was led by Sir William Penny. His report identified the instrument placement, the unnecessary second heating, and the organizational failure of self-regulation. Prime Minister Harold Macmillan classified it as top secret. For 30 years. The public received a sanitized white paper stating that no harm had come to the population. The reason for the secrecy was not domestic. Britain was negotiating with the United States Congress to restore nuclear cooperation severed by the McMahon Act a decade earlier. An admission that Britain's reactor had burned out of control would have ended those negotiations. In 1959, Parliament passed the Nuclear Installations Act. Before 1959, the organization that built and operated the reactor also judged its own safety. Sovereign immunity, no external oversight. After 1959, an independent Nuclear Installations Inspectorate with the legal authority to license, inspect, and shut down any nuclear facility in Britain. Before 1957, occupational radiation exposure was permitted at 150 millisieverts per year. After 1959, 50 millisieverts per year. The United States would not separate its own regulator from its developer for another 15 years. Britain got there first, because Britain burned first. There is one detail that hasn't been mentioned. During construction, the physicist Sir John Cockcroft insisted that massive filters be installed at the top of each chimney. The project managers called them a waste of money. The site engineers called them ugly. Everyone called them Cockcroft's follies. On October 10, 1957, those filters captured the majority of radioactive particles before they reached the atmosphere. Without them, the contamination would not have been limited to 500 square kilometers of farmland. Modeling suggests it would have rendered much of northern England uninhabitable for decades. A Chernobyl 29 years before Chernobyl. The thermocouples failed. The scanning gear jammed. The CO2 extinguisher fed the fire. The cooling system became a bellows. Every safety system that had been engineered into the reactor failed. The one thing that worked was the one thing they laughed at. The reactor still stands at Sellafield. Inside it, 15 tons of fused uranium remain, too radioactive to approach, too entangled with the graphite to extract. The graphite still holds Wigner energy. The water used to extinguish the fire may have created uranium hydride, a compound that ignites on contact with air. Decommissioning is expected to take until 2012 at a cost exceeding £120 billion. All within protocol, all signed off. and the air still moves through Sellafield, as it always has.